Now let us have a more specific example for transformation of the distribution of a point in a 2D plane represented by Cartesian coordinate versus representation in polar, and see how things will evolve. So in this example, suppose that I have, I'm transforming from Cartesian to polar for a circular symmetrical distribution. Then next we'll look at a distribution which is not circularly symmetrical. So if the distribution of x and y, fx and y, is circularly symmetrical, it means that this is a function of r, and r is equal to x2 plus y2, which means that this distribution is not a function of the angle theta. That means that if you rotate your 2D plane arbitrarily with any angle, the shape of your distribution remains invariant. So, so we say that a pair of random variables have a circularly symmetric joint PDF about the origin if we have this relationship. If the joint distribution is only a function of the distance with the origin, is not a function. So in this case, this is a general formula we have obtained. So we can find the joint distribution of r and theta, put it in this relationship. So because this is only a function of a square root of these plus a square root of these, so these will become r f r and times g of r. So, and this is for r positive. So obviously you see that the distribution, the joint distribution of f of r and theta is constant versus theta. That means that distribution of theta is uniform between minus pi and pi. So summary again, we get this expression from here. And then we see that this is only a function of, is not a function of theta. So if you find distribution of theta, you have to integrate with respect to r from 0 to plus infinity of r g r d r. Okay, so this will become, this is not a function of theta, so it's constant. So because this is non-zero for theta between minus pi and pi, so it's constant, so it should be 1 over 2 pi, and is 0 otherwise. Moreover, I could say that because this guy is equal to f of r and theta of r and theta is a function of r, a gr, times 2 pi and times 1 over 2 pi. So this is distribution of f of theta, this is distribution of r, so therefore they are independent. So here I say that r and theta are independent. And this guy is the distribution of f of r is equal to 2 pi r and then g of r. So in this example, we quickly were able to find distribution of r and distribution of theta, provided that we know that they have a joint symmetrical distribution. So so we get to these two expressions. So for all circularly symmetrical PDF, joint PDFs, we could immediately conclude that r and theta are independent. And this theta has a uniform distribution. and distribution of these is found like that. So circular symmetry quickly gives you the marginal distribution of R, marginal distribution of theta, and we know that they are independent. So this example is very important in practice. Remember that because theta is uniformly distributed like that, tangent of theta, so this guy has a Cauchy distribution, because if this is uniform, so let's say W is equal to tangent of a uniformly distributed random variable. In one of the examples of previous chapters, we have shown that this should have a Cauchy PDF. I remind you again that R and theta are independent.